AP scholars, you got to deal with the weight room noise here as I go through 8.6 to 8.9. Question 1, we're talking about some KBs and we're given different values. And the essential question is, what is the difference for the value of the KB? Well, obviously the differences in each of these compounds is what is bonded to this carbon. Here we have a hydrogen, here we have an iodine, here we have bromine. And the difference in strength of acids or bases is always their electronegativity. So C is the correct answer. All right, so I almost feel like they were announcing this one. So we're giving some conjugate acids, and we're asked again about the strength, which of the following bases has the largest value of Kb. Okay, so it depends again on electronegativity, and so out of the acids here, we have chlorine attached to nitrogen, we have oxygen, we have hydrogen, or nitrogen. No, yeah, we're going to say that, and then we have carbon. Okay, so out of the things attached to nitrogens, the highest electronegativity, the lowest electronegativity would be the carbon. So the carbon, then having the lowest electronegativity is going to make the strongest base. Wow, I'm really struggling to talk. Okay, so again, nitrogen attached to nitrogen, oxygen attached to nitrogen, chlorine attached to nitrogen, carbon attached to nitrogen. Carbon has the weakest electronegativity, and that means it's going to make the best base. So Kb would be the greatest for CH3NH2. All right, so we look at these pictures. The gray circles with white circles are our acids. The gray circles alone are conjugate bases, and hydronium is the black with 3 whites. Okay, so we're also told about 3 acids: HIO, HBRO, HClO. All right, so with acids, we want stronger electronegativity would be a stronger acid. All right, so we want to know each particle, based on the information, which particle diagram best corresponds to the indicated acid. All right, so out of these 3, HClO is the strongest, so it should have the most hydronium. That's in 3, so that eliminates A as being right. B is talking about diagram 2. Well, I just said that HClO couldn't be that. It's got to be this one. Okay. Now it says diagram 2 is HIO. Well, out of the 3 of them, HIO is the weakest. It should have the least hydronium. That is this one. So C is correct. A student pours 10 ml sample of acetic acid, pKa is about 4.8, to sodium acetate into a tube. The student adds a few drops of bromocresol green to the test tube and observes a yellow color, which indicates that the pH of the solution is less than 3.8. Based on the result, which is the following was true about the relative amounts of acetic acid and sodium acetate in the original solution. All right, so obviously if the pH is low, we must have more, it's below pKa, so we're got to be below the half equivalence point, because the pH would equal pKa, and that must mean that we have more acid than conjugate base, so A is the correct answer. All right, so we're given this titration curve. We're told that we're titrating glycine and dilute acid with sodium hydroxide, and based on the data, which of the following species has the highest concentration of glycine with a pH of 7? Well, pH of 7 is going to be up here, right? So that means we've got to have way more conjugate base. So if glycine is this, then the conjugate base is that, and that's what we're expecting. So the B is the correct answer. All right, number 6. Benzoic acid has pKa 4.2, molar solubility is 0.00278. Sodium benzoate has molar solubility of 4.16 molars. Several 50 ml samples of 2 molar sodium benzoate are treated with 3 molar HCl. The pH is recorded, and any solid crystals are filtered, dried, and weighed. The data from the experiment are given in the table above, which the following best explains the results. Okay, so bear with me. So the pH at the end is very low, and so that means that the pH is going to be less than pKa, and if the pH is less than pKa, then the concentration of the acid is going to be higher than the concentration of the conjugate base. So I'm thinking, hey, okay, yeah, pH is less than pKa, acid is less than conjugate base. Now, as far as precipitation, they told us that we were getting materials, so I wouldn't worry too much about that. But the reason why it's got to be the acid, because the acid had a low solubility, and it has a higher concentration from here, so we'd expect it to precipitate out. Realistically, without even talking about the precipitation, okay, if the pH is less than pKa, then there's no way the conjugate base is greater than the acid. Okay, so we know the pH is not greater than pKa, so that eliminates C and D. So really, it had to be A just on that basis alone. Number 7, a buffer solution is made with acetic acid and sodium benzoate. Sodium acetate, which the following equilibrium can be used to support the claim that the addition of a small amount of sodium hydroxide to the buffer will result in a very small change. All right, so if I'm adding hydroxide, then something has to be neutralizing that right away to eliminate it. So it's got to be an acid reacting with it. So we're going to say that the acetic acid is going to react with hydroxide to make more of the conjugate base in water. So that's why it's going to buffer, because of that action right in there. B is the answer. The acid ionization of hydrofluoric acid, and here, student claims that the pH of the solution contains 0.1 molar HF and 0.1 molar sodium fluoride will change only slightly when small amounts of acids or bases are added. Which of the following pairs of equations can students use to justify their claim? All right, so if I'm adding an acid, then I need the conjugate base to react with it. So that would be this reaction here, where the fluoride ion, it being the conjugate base, reacts with the acid to make HF and water. And conversely, to react with a base, we need the acids, and then we would take the HF plus the hydroxide from the base to make water and fluoride the conjugate base. Okay, so there's the buffering going on. All right. We have CH3 and CH3 dimethylamine. Okay. Kb is 5.4 times 10⁻⁴. The student claims 100 mils. Student mixes 100 mils of 0.2 molar methylamine with 100 mils of 0.2 molar methylamyl chloride, and claims that if a small amount of strong base is added to the mixture, then the resulting change in pH of the mixture would be smaller than the change in pH would result from adding the same amount of strong base to 200 mils of 0.2 molar. And which we found best explains whether the student's claim is correct or not. B. The claim is correct because the mixture contains a significant amount of the conjugate acid, which can react and partially neutralize the strong base, thereby reducing the change in pH. In 0.2 molar methylamine, the concentration of the conjugate acid is very small, therefore the strong base is not neutralized and the change in pH would be larger. So yes, B is correct. All right, number 10. All right, so we're told that, what do we got here? We're given this table with pHs, which of the following can be used to correctly calculate the pH at 25 degrees, that is 0.1 molar methylamine and 0.1 molar methylamyl chloride. Okay, so these are the conjugates, right? So we have equal amounts of an acid and a conjugate. that puts us right at the half equivalence point, which means the pH equals pKa. So since we have Kb, to find Ka, we would take 1 times 10 to the -14th, divide by this. So I see that going on right here. And obviously to get it as pKa, I have to do negative log of Ka. So A is the correct answer. Getting there. All right. We're told that for this reaction, pKa is 4.8, which of the following is the best estimate for a pH of a buffer prepared by mixing 100 mils of 0.2 molar of the acid and 100 mils of, all right, let's see, well, that's butanoic acid and sodium butanate. But we have more of the acid than the base, so that means the pH should come down a little bit. So from 4.8, we could safely assume that 4.5 seems reasonable to go down because we have more acid than base. Obviously, it wouldn't stay at 4.8, it wouldn't go up. And 1, that's a big drop in the pH. That's not going to happen. So without doing any calculations, B, definitely the best choice. All right, and again, we have 40 mils of 0.5 molar lactic acid, okay, and sodium lactate. All right, so we have 200 mils of 1 molar sodium lactate. That's the conjugate base. So I have way more base than acid. So if pKa is 3.8, more base is going to make that go up. And so the question is, how much is it going up? All right, well, let's see. We have, let's see, 40 times 0.5 is about 20 millimoles here, and 200 millimoles. So we have 10 times more base. That means that we're going to bring the pH up by a full unit. So it would be 4.08 D, final answer. All right, now we come to our FRQ. All right, first thing is drawing a Lewis structure. All right, a little review is comparable. Let me switch screens and start talking about that some more. All right, so the first thing is to draw the Lewis structure. Well, carbon always makes 4 bonds, so that's pretty obvious. Nitrogen usually makes 3 bonds and has an extra non-bonding pair, so we should have that. All right, in the next part, we're told that we have a 2.65 molar solution of methylamine. We're told that the pH is 12.54, so I could assume that means the pOH is 14 minus 12.54 or 1.46. So now I can figure out my hydroxide, which is 10 to the negative pOH, or 10 to the negative 1.46. Gives me around 0.0347 molars. Okay. So now I set up my ice table. I know my initial value of the methylamine is 2.65. Products are 0. I know the hydroxide is going to be 0.0347, so that means that goes up by 0.0347. That goes up by 0.0347. This goes down by 0.0347. Now, if you wanted to approximate and just say that this is still going to be 2.65, that's fine. They would give you credit for it. But since the numbers were there, I did this subtraction. I set up my Kb expression, and then I substituted in my products over my reactant, and I got around 4.6 times 10 to the negative 4. The rubric said that it would accept up to like 4.53 or something like that. So if you did the approximation, it would still be okay. All right, I'm gonna read the next one. So let me shift screens again. C. All right. So in part C, we're looking at this titration curve. We're told that we had 25 mils of the base with 1.84 molar HCl, and very specifically at the equivalent point, we're using just over 28, so we're at 28.25 milliliters of the acid. We want to know the concentration of base. Well, at the equivalence point, MaVa equals MbVb. Now, let's shift screens. Okay, MaVa equals MbVb, 1.84 times 28.25 milliliters equals Mb times 25 milliliters. When we multiply and divide out, we get 2.08 molar. All right, then we're supposed to draw in a beaker a solution that happens when we add 5 milliliters of the titrant. Okay, So if I'm out here at 5 milliliters, okay, I have to have way more of the base than its conjugate or anything. So the base is the gray, the conjugate acid is the white. So I have to make sure that my drawing has more shaded areas than non-shaded, okay, which is why I this. Now it didn't matter how many, as long as there was more shaded than unshaded. And finally, explain why the titration curve shows only a small change in pH per volume of acid added when the total amount of acid added is about 14 milliliters. And include a chemical equation as part of your answer. All right, so we have to remember that we were talking about an acid and its conjugate base, especially all through here, right? So it's buffering. So what does that mean? All right, let me shift screens again. So what it means is that when we add an acid, the base is going to neutralize it and make a little bit more of the conjugate acid. But in the buffering sense, that means that having more of this is just going to shift it back. So we're kind of like balancing it out. The acid takes away some of the base, but then we shift it back and make a little bit more. Okay, so really this was the reaction you had to write. Okay, you had to understand that when we take the base, the acid is going to react with the base and make its conjugate, and in this case, water. All right, that was a long one, and I have one more to go.